Here's the Cybertek. It comes in a nice carrying case. Get the handle and so forth, and it's well protected. And when you open it, it's got a little compartment for your BNC to micro grips, and then it has another BNC to BNC, and then you have this the CK100 injection transformer. You got the input and the output. It looks like it's an extrusion case. It's metallic, and it's got a ground case here. So it looks small, compact, and this BNC looks like it's attached to the case, and this one, if you notice, it's got the insulator, so I believe that this is floating, so that kind of makes sense. Okay, so we're going to go ahead and inject a signal and take a loop measurement of a power supply, see how well it performs. And looking at the data sheet, you can see that on their Cybertek website, we have the CK100 wideband injection transformer, and it has a bandwidth of 2 hertz to 2 megahertz. And I believe the DC current that you can source before it starts saturating is 10 milliamps. So we can go to the specification, take a look at that, and sure enough, it's DC current, so you can put up to about 10 milliamps. And typically this would be at a specific frequency, although it's not specified, but we can probably measure that. It's a 1-to-1 ratio, and it can isolate up to 600 volts. It's a Cat 3, and the input to output capacitance is 400 picofarads at 100 kilohertz. We'll be able to measure that. As far as the instructions, here is, I believe this is probably the instruction manual. Here's the picture. Here's the in and out, 1-to-1, 2 to 2 megahertz. And it comes with the BNC to alligator clips or micro clip connectors, and also another BNC to BNC. Again, here's the specifications, and it actually comes in a nice carrying case. So I'll show that as well. Anyway, that's the data sheet on that. Okay, I have the power supply here. It's approximately a 30-watt supply with 30 volts, 200 volts, and 400 volts. So it's a multi-output power supply. And I have my my test probes here from Omicron, and the injector goes right here, and it's already been calibrated. Then I go ahead and put the input. So I'm going to do a Bode plot, and then I also want to monitor the input current to see where it starts modulating. But right now I'm interested in obtaining a Bode plot, and I'll do a Bode plot from 1 hertz to 100 kilohertz, which is the switching frequency of this power supply. Okay, I have this CK100 connected to my little power supply, so I'm going to go ahead and start taking the Bode plot. So I'm going to sweep it from 1 hertz, which is the lowest frequency that the Bode 100 can measure, and I'm limiting to 100 kilohertz, and I'm putting about 0 dBm millivolts, and my attenuation is 20 dB. I can probably go down to 10, and I'll try that in a little bit. And I'm going to set the bandwidth to about 300 hertz. So I'll go ahead and press start, and it should start taking a plot. So as you can see, below 2 hertz, there seems to be a little bit of a noise around this area. And the bandwidth calls, or that is stated, is 2. So you can see the red goes up and down a little bit. But then here at 2, then you can see that it seems to be straightening out. So you have much less noise. And it looks pretty good once you get at 2 hertz, which is what is its manufacturer is specifying. It looks very good. There you go. And then there's a little bit of noise at 60 hertz, which is to be expected. Okay, that looks good. It's a good measurement. So let me see what happens. Usually, if you increase the voltage, you might get some saturation, so you might get some sag. So let me go ahead and go full power, which is 13 dBm on the Bode 100. And I can see, looking at the scope, I'm looking at the current, it has a little bit of saturation. But the Bode 100 can still filter any of the harmonics out, and it still takes a decent Bode plot. As a matter of fact, it looks, because of the increased amplitude, you have a little bit less noise below 1. Looks good. Now it might, because I'm putting a little bit more voltage or more amplitude, this might change. Typically, if you overdrive it, you will change the Bode plot. And the rule of thumb is, if the crossover changes quite a bit, then you know that you put too much signal into it. As you can tell right here, there's a little bit of difference. And I still have a little bit of saturation, even at 1 hertz, no, 10 hertz. But it's still filtering. The Bode 100 is still able to filter the harmonics, and then right here it stops us saturating. So that looks good. So there's a little bit of a dip here, and I think that's because it's saturating. And if you power or pull back on, go ahead, let me save that. But if you go back and reduce the power, then you should get, this should go up. So it's a little bit of a compromise. You either increase the power to, let's say, take a reading at low frequency, and then you can decrease the power at this level. And you can do that by using the variable state. Right now I'm using the constant. output. So this is at 13 dBm. And let me make this a little bit thicker so you can see better. And so we're at 0 dB. And surprisingly, the Bode 100 is able to filter out even when you saturate. It looks like the amplitude is still good. What changes is, let me see, the phase. There is a little departure right here. Okay, so here's the difference. There you go. So this is at 0. This is 0 dBm. So as far as the valid one, I would believe that the 0 dBm, which has less distortion, will probably be the valid one. If I decrease this, let's say to -10, let's see the effects. Let me go ahead and put this here. So this should be the current trace. And you should pick up a little bit more noise since you reduce, and yes, you do. But if you notice, the 0 dB is basically the same. So this tells you that you have approximately the right amount of signal going into your power supply. And I'll put this as -10 dBm. Okay, so there you go. So it does measure all the way to 2 fairly reliably. It's right there. And then depending if you overdrive the circuit, you can always tell if you're overdriving by where the crossover changes. So in this case, right here, you have minimal amount of change. So that means that you have a pretty, the right amount of amplitude signal going into your power supply. Okay, so now we're going to measure the impedance and the input and output inductances. So now I'm going to go ahead and connect the CK100. I'm going to use a 1-port measurement. I'm going to calibrate using a short, open, and load to calibrate the impedance using a 1-port measurement. And then I'll connect it, and I should be able to measure the input impedance of the injection transformer. And since they're 1-to-1, the same measurement that I get on the primary, I should get on the secondary. You should also be able to measure uh, the self resonance, if it's low enough, if it's below 440 megahertz, the Bode 100 should be able to measure it. So take a measurement. Okay, so now I have the Cybertek CK100 connected, and I'm doing a one port measurement using the Bode 100. And I have the source level at approximately negative 10 dBm. And this is the impedance of the Bode 100. I'm sorry, of the CK100. And I'm sweeping from 1 hertz all the way to 50 megahertz. So I'm going to go ahead and save that. CK TK100. So there's a little bit of a dip here. It's probably where it saturates. So I can probably lower this. Let's go to 20. See if it changes the measurement. And it does. So if you lower the excitation source, you're less likely to saturate the core, and therefore you'll have less likely of having a lower. If you notice, it does change up to right there. Let me see if I can change the color. Change the color to blue. Put the weight 5. So this was, I believe, at negative 10 dBm, and the red one is negative 20 dBm. So there's a little bit of a difference in the lower, but other than that, and this is just a little bit of noise. You can, this will go away if you increase the voltage or the amplitude of the source. Now, another thing that we can do, we can enable this. This will give you the inductance measurement. You can see that at high or very low, it has about 2.2 millihenries, or henries actually, and then it decreases. So right there where it plateaus is about 800 millihenries. So that's probably, if I put this here, that's 100 kilohertz. It's about 700 millihenries is right there. That would be the plateau. Now, let me see if I can get a, I'm going to go ahead and see what happens at 0 dB. So there's a little bit of saturation, I believe. Okay, so now I believe can do a add fit, and so automatic best fit. So this is the model. So this is the actual plot, and using a very simple model, it generates this type of plot, and these would be the model that you would use, and these are the values. So in this case is using a 621 millihenry, and the self-resonance is 14 puffs, and the impedance at self-resonance is 157K, which would be correspond to the top. So and right there, that is the curve fit model. And we can make it a little bit let's make the weight a little bit heavier. So that's the curve fit. So there is some discontinuity or some effects here due to saturation. Now, I'm just curious if we use a different model. It says simple and then network. Let's see what this does. And this looks like, what is this? It says real and then the complex pole. And oh, actually, if you notice, this does generate a curve fit that's closer to it, and you can see that here. Let me turn this off. Okay, so this is a little bit better. So that's the impedance, and then this generates roughly about 846 millihenries at 1 kilohertz. Is it 1 kilohertz? Let me see. Yes, so it's 1 kilohertz here, or 974. 1 kilohertz, close to. Actually, I can do. And that's 810. Curve fit is 846. So that's pretty good. Okay, so now I'm going to see if I can measure the transmission loss. Now I'm doing a transmission gain measurement. Both the input and the output are terminated at 50 ohms. So this should give you kind of the bandwidth of the injection transformer. And you can tell at approximately 1 hertz, you have a little bit of attenuation. and then it flattens out at about 2, 3, 4. That looks pretty good. So let me make these visible. So if this is your baseline, that would be your 0 dB right there, or 3 dB. Then I can move this. Okay. So from this measurement, it looks like the lower 3 dB is 3.9 hertz, which is pretty close to the 2, and the upper is actually a little bit higher than its stated upper frequency. Upper frequency states is 2 megahertz. In this case, it goes up to 5.4 megahertz. So that's pretty good. So we'll go ahead and make this 5. There you go. Now let me go ahead and extend this up to double the frequency. See if there's any difference. Go ahead and lower this to 10, to a negative 10 dBm. Okay, so it's about the same, and it does have a like a anti-resonant and another resonant point here, but past this point I wouldn't use it. Although the flatness here is fairly good, and it looks like it is very close to its stated specification. Other than that, it looks like a good injector. Uh, might have a little bit of a saturation in the lower frequency, but most injection transformer, all of them have a certain limit, lower limit, and they just keep in mind that the injection transformer or all transformer are not meant to work at DC. They're meant to work at a certain frequency, and the lower or the larger the inductance, the better it tends to work. There you have it. This is the demonstration demo of the CK100 injection transformer. If you have any questions, send to my email and I'll try to get back to you. Thank you.